Today's lesson is on similar triangles. Similar triangles are similar in nature to the idea of congruent triangles because in both similar triangles and congruent triangles, the triangles are the same shape, that is, so corresponding angles are congruent. The difference between similar triangles and congruent triangles is that the two triangles do not necessarily have to be the same size. Even though all three corresponding angles are congruent, corresponding side lengths may differ. Now those side lengths will still be what we call proportional, but we'll talk more about that in a little bit. Symbol-wise, the tilde symbol, which is also the top of what you see on a congruent symbol, that little part of the congruent symbol all by itself means is similar to. So here we have a picture of Dr. Evil and Mini-Me. I think you could certainly argue that they are the same shape, and most certainly can argue they're not the same size. Therefore, you could say Dr. Evil and Mini-Me are similar to each other, and in math symbols you could write Dr. Evil tilde Mini-Me, meaning Dr. Evil is similar to Mini-Me. So in similar triangles, we find that just like in similar triangles, the corresponding angles are congruent, and the corresponding side lengths are what we call proportional. So let's dig a little bit deeper into that whole concept of proportionality. What I've done here, I have made three ratios consisting of the 6 side lengths. So each ratio is a side length on the blue triangle over its corresponding side length on the green triangle. So we have the shortest side of the blue triangle being divided by the shortest side of the green. We have the middle side of the blue triangle over the middle side of the green, and we have the longest side on the blue over the longest side of the green. Those are corresponding sides. So what I'm going to do then is do the math here and find out what each of these ratios ends up simplifying to. Each of these ratios ends up simplifying to simply 2. Meaning each side of the blue triangle is exactly twice the length of its corresponding side on the green triangle. That allows us to conclude that triangle ABC is in fact similar to triangle CED. Here are the same two triangles. They're still similar to each other. When you write a similarity statement, just like you would a statement that shows congruency between two triangles, the corresponding congruent angles must be put in the same order on each side of the similarity sign. So triangle ABC, it doesn't matter if I call that ABC or CBA or BAC or whatever. What does matter is once I establish that I'm going to call it A, B, C, I better be darn sure that in my second triangle I list the vertices in following the same order. So like how angle A here is the upper left angle. Angle A here is between the short and longest sides. That's what I led off with. So I've got to lead off with my angle C here because that is the angle on this triangle between the shortest and longest sides. Angle B appears to be a right, back there you. Angle B appears to be a right angle on this triangle, and that comes second in the name, so I'm going to use the angle that appears to be the right triangle and here, angle E. C is left over, so I use D here. So the ratio of a side length on one triangle to a corresponding side length on the similar triangle is known as the scale factor. And we just found out that value a moment ago with these two triangles. We found that the scale factor going from big triangle ABC to little triangle CED is 2 because each side was exactly twice as long as its corresponding side on the green triangle. You could also look at it the other way. Going from the small triangle to the big one, the scale factor would be 1/2 because each side on the small triangle is exactly 1/2 the length of its corresponding side on the big triangle. So let's look at an example using this similarity concept. Here they are flat out telling us that triangle nah is similar to triangle yup. So here we're given, in this example, we're given a little bit of information about the side lengths of a couple different triangles. And really the most important piece of information here is the fact that triangle NAH is similar to triangle YUP. Now I could sit and draw a diagram of these two things, and honestly, I wouldn't fault anyone a darn for doing that. In fact, I'd normally encourage it. But just to kind of show you that how important the order that you write these similarity statements is, just to show you the importance of that, I am going to use nothing but this similarity statement to solve this problem. So they give us two similar triangles. They give us 4 of the 6 side lengths. It looks like 2 on each. Yep. 2 on each, and then they ask us for the side lengths of the remaining unknown sides. So that will be 1 side per triangle. Now, since we know these things are similar, we can safely say that the side lengths, the corresponding side lengths, are proportional. So it's really just a matter of figuring out which sides are corresponding so that you can write your proportions. That's where the trick lay. You have to figure out which sides are corresponding. And I'm going to use the congruency statement to do that. Here we can see that side NA will correspond with side YU. Side AH will correspond with side UP. And side NH will correspond with side YP. It's those last 2 that are going to be a great place to start. NH and YP correspond, and it just so happens they give us the lengths of side NH and the side YP. That also tells me then, since they're corresponding sides and I know both their lengths, that tells me what the scale factor is between these 2 triangles. For every 20 units that you have on the left triangle, you will have 35 units on the right triangle. Make a ratio out of that scale factor. You can then project that to whatever it is you want to know. Here they tell me about side UP being 24.5. Side UP corresponds with side AH. So I'm going to make another ratio out of those 2 side lengths. The question I need to ask myself is, which do I put on top? Do I want AH on top from the first triangle, or do I want UP on top from the second triangle? The answer to that question is, what did I do for the first fraction? For the first fraction, I put NH on top. NH came from the first triangle. So I need to make sure I continue putting information from the first triangle on top in the second fraction. So that would be side AH comes from the first triangle. I'm going to put that on top in my second fraction. That corresponds with side UP, which I know is 24.5. From here you can cross multiply 20 times 24.5 has to equal 35 times AH. 20 times 24.5 is 490. And if you divide away the 35, you should get 14 units for side AH. Now I still need to find the length side YU. I don't know what side YU is. I'm still going to start out with my 20 over 35 ratio because that scale factor doesn't change. 20 units on the first triangle represents 35 on the second. I want to put NA on top, which is 16 units, and NA corresponds with YU, so I'll put YU on the bottom. Again, the reason I put 16 on top is because it comes from the left, or the first triangle. The reason I put YU on the bottom is because it comes from the second triangle. And since that's how my scale factor is set up, I need to be consistent with that throughout the problem. If I cross multiply here, then side YU is 28 units. But these problems are nothing more than just figuring out the scale factor, setting it up as a ratio, and then building a second ratio to make a proportion, and cross multiplying.